No, no,
Ah, sì.
lo posso dire.
Se non metto... Speriamo non ti pianti tutto.
Alors, j'ai repris sur Chrome.
Oui.
Je vous entends, j'ai déjà reçu les slides. Maintenant, reste à voir si on peut transmettre la vidéo.
Ok, ce l'hai?
Qui devo entrare in modalità presentazione oppure...
Sei già in modalità presentazione. Prova se funziona.
Ok.
Okay, good morning to everybody. So today we have a presentation from Juri Lelli. Juri Lelli was a PhD student at Scuola Superiore Sant'Anna, where I was until last year, and he worked on modifying the Linux scheduler for introducing some new real-time scheduler. And all these efforts have been successful, in fact, because the scheduler is now distributed with the Linux, the stock Linux. So if you download a new Linux, you will find his work inside the kernel. And after his PhD, he started to work at ARM, and is now working mostly on energy and how to use the new scheduler to save energy and reduce the power consumption of embedded systems. Okay, so thank you, Juri, for coming. And
Okay, thanks to everybody for coming. I'm sorry, I don't speak any French, so I hope my bad English is still fine. So I also tend to speak too fast, so if you please interrupt me. Also, because I think this presentation is, if we keep it as interactive as we can, it's good, because it's basically my experience with the Linux scheduler. I will give you some details of what we are doing and what I basically did in my, let's say, previous life. But anyway, if you have any question, please interrupt me and we can discuss the thing. So yeah, so this is basically what I intend to talk about this morning. I give a slight introduction on well, who I am, and then the Linux scheduler in general. Then I'll talk about what we are doing, what we basically did before I joined in ARM, and what we are doing right now. And then I also refresh a bit the thing. I think Pepper already told you what the deadline scheduling is, but anyway, I give you a very overview of the thing, and then I guess this is the whole purpose of this thing. I mean, I'll present to you like open questions that we have currently at ARM, and maybe we can like really afford time in investing, and maybe someone who is interested in this kind of thing can help us to answer some of these questions. Okay, so let's get started. So who I am? Pepper already mentioned this. I did my PhD at Retis laboratory in Pisa, and basically focused my research on multiprocessor system and general purpose operating system. In this case, it's Linux. Because there was, when I joined the PhD, there was this long time effort on modifying Linux, so basically adding some more real-time capabilities to the stock Linux scheduler. and was kind of lucky that I basically joined in the time that this effort was basically was 5 years old, more or less, when I joined. So in the last maybe 2 years of my PhD, I could take that thing, and then we got it accepted into Linux. But I'll get back to that. Yeah, I mean, as part of my PhD, I had to, of course, attend the conferences. I had at the time, the pleasure to go to Linux focused conferences. I don't know, maybe you heard about the Linux Plumber conference and this kind of things. Basically, they do this kind of conference once a year, and they discuss there all about basically the things that needs to be done to enhance the capability of Linux. And you have to go there to convince them that what you're working on it's valuable and can benefit Linux as a whole. And the other nice thing about this conference is that you speak to a guy working like in industry. So I also find a job because yeah, you speak with people working in this case in ARM, and the just basically call them and say, yeah, I'm still working on this, and you get the contract. So right now I working for ARM last July, and so I'm still working on Linux. Maybe, well, not right now, but maybe in the future I will keep working on real-time aspect. But right now we are focusing on the best effort Linux scheduler, and we try to modify it to be more power efficient, or at least power aware, power performance aware. I'll talk about this in a while. So yeah, why I'm here? I'm here basically to personal experience, as I said, because I was lucky to be part of the effort, the research effort that actually then contributed to the Linux scheduler kernel. And right now I'm part of the same kind of effort, so they're working on this thing for the last 4 years, more or less. And right now we are receiving positive feedback from the mailing list and the kernel maintainers. So I won't say anything, but I mean, it resembles me what happened like 2 years back in time when I was in Pisa. So let's be positive about this. Yeah, so we are basically focusing on heterogeneous system, single instruction set architecture system with a lot of effort on the big little system. Maybe you're already aware of what it is, but I'll give you some information in the following. And I'm personally here because I'd like to give you this overview and maybe try to interest you on something that we're working on. So then basically the research question that we can't answer right now, or we can say we will spend like the next year working on, maybe you can do because you are, I mean, research entity, so that's it. And yeah, of course, because Giuseppe invited me, so thanks for that. Okay, so let's start. Yeah, okay. So I don't know if you are already familiar with the Linux scheduler, but anyway, I guess this is the most simple overview of how the Linux scheduler is implemented. It's basically a framework. It's a modular framework in the sense that basically you have a core that resides in, basically it's implemented in a file, but it's core.c, so it's pretty obvious. And then on top of this, you can basically plug different kind of scheduling classes. Those are basically, right now you have deadline RT, that is real time, and also deadline real time, fixed priority real time. And then you have fair, that is best effort. And those scheduling class can implement one or more scheduling policies. So for example, the shed normal is the default of Linux. Basically, everything is scheduled by this shed normal. That is basically best effort fair scheduling. And you have real-time policies, and those are over here. Basically, a policy, it's an implementation of some scheduling rules. So you say, yeah, basically they decide which process to run next and on what processor, basically. Okay, so this is the overview. Okay, so we'll talk in the first half of the presentation about schedule normal. So it's the best effort scheduling policy. This is implementing fair scheduling. It's a weighted proportional fair scheduling. So basically you can associate a weight to your task, and then if the weights are all the same, you get basically the same amount of CPU shared among every task. So you want to be fair as possible. And the intent here is to basically it's toward performance. So you want the best throughput you can get without giving any you can say anything about the task. So it's just best effort. This is the default scheduling policy. So if you run Linux or maybe on your cell phone, because you're running Android, basically almost all your tasks are scheduled by this policy here. Yeah, this is somewhat a recent contribution by Google and Turner in this case, working for Google. They added this PEL, so it's per entity load tracking. So you can somewhat estimate, so you can actually track what's the load of your task. So let's say you start some workload, and after a while you can say, okay, this task comes at this amount of load. And this is basically, it works using the system. You keep track of this thing, and then you can maybe do something with this information that you try to extract from the system. The nice point of this load tracking is that it's frequency invariant in currently in mainline. So that means that if your CPU run a different frequency for frequency scaling needs, the load that you get from this thing is always the same. So you don't see any variation. So you can say, okay, this task, I don't know, it's 50% load, and you can say this is 50 at I don't know 1 gigahertz or at 300 megahertz. And this is nice because you can do basically scheduling decision without considering the exact OPP that you're running at. This is kind of handy. What we did, and this is under discussion currently on the mailing list, it's actually to get this system load thing also micro arc invariant. So the problem that we face is that basically we have these two kinds of CPUs, and let's say one runs, it's like running faster than the other, so you get basically different kind of load if you don't scale properly, considering these differences. And what we are proposing is to introduce this second kind of invariant to be able to do the same kind of scheduling decision. So I can say the task that runs on my big CPUs can run on the little, and I see the same kind of load. But we'll get back to this because it's part of the thing that I'm going to talk about. Okay, any questions so far? No.
So the load you are estimating here is the execution.
Yes.
That you measure execution and then you compute the load.
Yes.
So it actually depends also on the total
of course.
amount of tasks in your system.
So yeah, actually you get both, well, it's like naming, but you get basically two signals. One is load and the other one is utilization. And this load is basically, yes, very much affected to the basically load experienced by all the other tasks. This utilization is less affected by this because it's a completely different way. But in certain cases, it's, let's say that the utilization signal, and this is the signal we are like working, using in this work, it's only useful when the system is not overloaded. I mean, when the system is full, you can basically say anything about your task because everybody's running and is sharing the CPU, so you don't know. But if you're under this overload scenario, you can use this thing and you track in the
When you
runtime.
are not overloaded, this is a good approximation of the required load.
Yes.
How much you need to execute. When you are in overload, this is basically the share you get.
Yes, exactly. Yep. Okay. So, heterogeneous multiprocessor scheduling, what does it mean? So let's say this is our problem space. So let's say you have a system composed of different types of CPUs. And those are basically all the latest core by ARM. So let's say you have, for example, a big CPU, or let's say a cluster of big CPUs that are very powerful. So they can run very fast, but they consume also a lot of power by running so fast. And example is, for example, the Cortex A57 or A72 that will be forthcoming. And together with this, you have another cluster composed of little CPUs, and they are very energy efficient, but they can sustain high computing demands. So let's say that you can, I don't know, run high demanding video games or this kind of workloads on those because they can actually provide the necessary capacity. An example is the A53 or it was the A7 in the past. So on top of this, you run Linux, and in our case, it's basically Android. So basically, it's Android cell phone that has this kind of CPUs and run Linux. So you have Linux is like the operating system. On top of that, you have Android that basically use Linux for doing scheduling stuff. So it's basically Linux. The problem with this kind of situation is that you have a fair control of Linux in the sense that you can, source code both it's available, but you can basically modify Linux and then try to basically put your changes upstream. You are not so free to do the same thing with Android because basically it's Google controlling it, so it's not that easy. The problem with Linux is that right now has no notion of heterogeneity, so you cannot see if you have this kind of different type of cluster. It sees basically if you run stock Linux on this kind of processor, you see just as SMP processor. So you have, for example, if you have a cluster of 2 big CPUs and 4 little CPUs, you see 6 CPUs, and Linux will try to spread all the tasks everywhere, so you get really bad for power consumption and also for performances, because you run stuff that has to run on the big CPUs on the little. So you cannot just use Linux. And the other constraint that you have when you are working on Linux at the kernel level is that all your solution that you can come up with has to be fast. So usually they're also quite simple in its principle because you cannot, let's say it's not so easy to come up with a very efficient and fast solution to put there. Yeah, so for us, basically, Android is a bit of a black box. So you get it running stuff, but you don't get direct information from it to the scheduler, to the kernel in this case. What you can do is using those pelt stuff to get some information from those tasks and then try to schedule them accordingly. And the other problem with Android currently, maybe this will hopefully change in the future, is that they usually don't want anything that is not shed normal, because they basically say, okay, if you run shed 5, or real-time priority, you can basically run, you can screw all the other tasks. So basically using shed normal, they are pretty comfortable with saying you won't starve any of your tasks. I think that the thing will change if they use shed deadline, but we'll talk about this later on. So the big question is, how do I meet the computing needs of my task while at the same time I save energy? And this is what basically we are trying to address. And yes.
So when you say Android is a bit of a black box, it means that from the user application you have little information about what's going on.
Yeah. So basically, right now it's Android's. Let's say of the old mechanisms you have right now to basically inform the scheduler or the kernel in general about the information about user space. I don't know, you can use C groups, for example. They use C groups, but just they have a background, foreground type of thing, and that's it. So it doesn't say anything. They actually, the weird part is they actually have a lot of information in the Android framework because they have basically a manager of activities and they keep track of everything that is actually scheduled. So they have a lot of information, but they don't tell those information to the level underneath. So
it's a black box both toward the user,
yes,
but also toward the kernel.
Yes.
So the kernel is difficult to get this information there.
Yeah, I mean, for a user, they have an API that developer can use. Maybe they can say something about the kind of priorities or stuff that they are interested in too, but then Android decides what to do and usually doesn't tell much.
So do you think that this is because they want to protect, let's say, the owner from intrusion,
yes,
from anything like this?
Yes. So
they don't give anything because they don't want the user or the application to mess up with this.
Yeah, also because I mean it's kind of different from what Apple does. So basically, they provide everybody with an API they can use, but that means that everybody can write any kind of application and then run the thing on the system. So if you give too much freedom, it's basically that everybody can mess your phone, and then it's not. I mean, if you install an application and then your phone doesn't work anymore, you won't go to the last person that you download the application to. You go to, I don't know, the person that sold you a phone, and eventually to Google saying Android doesn't work. But then it's not Android; it's the person that didn't write the application correctly. So yeah, I guess this is the problem that they are currently facing. I'm aware. I mean, there is a presentation. I guess last year, Google I/O. They were basically using Shed5, also real-time priorities, to schedule audio pipelines, but this is still done by Android itself. It's not the application developer that does this. But anyway, as I said, I hope that this will change in the future. We'll see. Okay, so this is our question here. Okay, so the first solution that ARM came with is called global task switching, heterogeneous multiprocessing. There are different names for the same thing, as far as I could understood. Well, the very first solution was actually something even, let's say, simpler in some sense, because they basically use the big little cluster as two basically completely separated stuff. So they were like running, starting just with a little cluster. So let's say you have 4 plus 4. You just see 4 CPUs at a time. So they will keep the little cluster on, and then as soon as they realize that the load, I mean the workload was too heavy, they switched off the thing, migrated all the stuff on the big, and run the thing on the big, and then there was called cluster switching. But then after this, also, I mean, they realized that if you have 8 CPUs, it's nice that you really see those 8 CPUs because it's a bigger CPU, it's bigger processor. So they come up with this global task switching, and yeah. So basically, those are the key features of this thing. I will just talk about this in this slide because I studied a little bit of the code, but I didn't really play with it. So anyway, they basically introduce heterogeneity in the scheduler by using CPU masks. So basically, you define at compilation time that those are, I mean, CPU 0 and 1 are your big CPUs, and CPU 2 and 3 are little CPUs. And then, so you basically know on which CPU you're running on, and you can do scheduling decision based on this thing. This is something that this Linux doesn't do. And also, this is something that won't ever be accepted in mainline because it's just focusing on a particular system. This is something that usually they don't like, the maintainers. And they were using Pelt to basically do the same thing. They were tracking load and base decision on this track load. Basically, you have some kind of a threshold. So you say, okay, I start on, I don't know, a little CPU, and then after a while, my load crosses this threshold, and I realize that I have to migrate the task to a big CPU to make it run, make a space for it. There was basically, so this is starting from Linux 3.10. So this thing is, let's say it's kind of the same version that you have right now on mainline, but with little changes, but it was the same thing basically. I guess the key fact that the key difference of this solution with respect to what we'll see next is that the big CPUs were used basically just as accelerators. So the idea was basically the rules were simple. So when I start a task, since I don't know anything about it at the beginning, I just start that on a big CPU because maybe it's big and I don't want to affect too much its performance. As soon as I realize this is not big, I put on the little, and then I run on the big only tasks that are really big, so they are crossing the thresholds. If I don't have anything like that, I keep those shut off. Yeah, the other rule, this was also configurable in some way, but they were try to pack little tasks as far as possible on the few number of CPUs. So as you may already understood, those rules were really working quite well on basically the CPU, the implementation that they have at the time, because there was, I mean, they are studying and they say, okay, this is the best I can do to have both performance and power saving. But those rules are not general in, but yes.
What do you mean by as fast as possible?
I mean that if you have, I don't know, 30% task, you try to let's say 150, 140% task, you try to pack in one CPU. And then if you have more that doesn't fit in the CPU, you have to use 2 CPUs. That's it. It's a simple thing. I mean, as soon as you have some spare capacity on one little CPU, you try to fill it. And if it doesn't fit, you have to use another CPU. So it was kind of, so it's fairly simple. But as I said, that was really effective on the system they had at that time. Yeah, so why, I mean, this was working really well. I mean, they were saving a lot of energy. And so why they didn't upstream it? Well, the reason, basically, it's what already said. So it was really tailored to the big list of systems of, I don't know, 4 years ago. So it was working really well to on the type of system, but it wasn't, I mean, you couldn't run the same kind of thing on another system, maybe not being little or anything like that, like an SMP system, because you don't have, but first of all, you don't have the 2 type of masks, and then you can maybe packing on an SMP with different CPU frag stuff. It's not always the best solution you can do. And yeah, so it was basically enforcing policies, so scheduling policies that were not general. So like the packing thing, for example, is not always the best thing you can do to save power. It depends on your particular system.
I think you should say that in the Linux development, there are two parts. One is dedicated to the specific processor, and the other one is totally general. And they try to keep the dedicated part as small as possible. So like assembler, counter switch, and a few other things.
Yes.
And they try to keep everything in the general part. So it's easy to modify something, but then it's difficult to convince the rest of the community that this modification has to be put in the general part.
Yeah, also because basically your solution has to work, or at least has not have regression on all types of systems that Reno can run on, from the big server farms, so NUMA systems and with, I don't know, thousands of cores, to the like real embedded stuff of a cell phone. So if you modify the core part of this scheduling framework to your needs, maybe you are like introducing regression on the far end of the spectrum of Linux, and that's not something that can be upstreamed, of course. So yeah, that's the big problem with this. So I guess we'll learn the lesson that you can change fairly easily Linux to suit your needs, and that can also work for your system. But then you can really expect that this solution will be taken upstream. And well, you may say, yeah, but why you are interested on this upstream part? I mean, it's not. Well, I guess the main reason is that because if it's not upstream, you have to basically keep maintaining your patch set and keep rebasing on the new version of Linux. So basically, this is quite an effort. And also, I mean, the nice thing is that if inside Linux, this kind of new thing that you put there, everybody has to basically ensure that also this thing is not breaking by any further changes. So that means if you develop a kind of a solution that suits your need, then nobody can in principle break it. So it will be always working good. And that's not something that you can assure if you are not part of the upstream kernel. So that's why we are interested into having this thing there. Okay, so there was the first attempt, and was working pretty good, but it wasn't possible to upstream this thing. So what I mean, you need a different kind of approach. So actually, what you need to be able to say, I really want this thing to be accepted into Linux. So you want to be there. So you want still a way to discern the computing needs of your task, because this is handy to say this task can run on a little, or else I need a big processor to run this thing on. I guess instead of just defining static configuration for your system, you maybe need a model of your platform that then you can use at runtime to do scheduling decisions based on the platform. And then the model is general per se, because it's really a model of the processor you're running on. So this is applied to any kind of processor and system. And then, also you need a fair plan on how to modify the Linux scheduler as is, in a way that, let's say that the maintenance doesn't get angry because you do, I don't know, too much modification, or maybe your modification are conflicted with other parts of the scheduler or anything. So basically what I'm saying is that you have to really understand how the load balancing is working on now and how it's implemented, to say, okay, I can modify that thing in particular situation to suit my need. And that's require time. Yeah, it requires a lot of time to basically understand the thing, how it's working now, because it's, I mean, the fact that it has to run fairly good on all this kind of system, it means that it's kind of complicated. And the documentation resides mostly on the maintainer's brain. So you can like try to poke them and say how this thing works. But I mean, they're pretty responsive in this thing, but you have to pose the right way. I mean, you have to interact with them once you get some kind of knowledge of what's going on. You can just go there on the mailing list and say, sorry, I don't understand, or I don't know how this works, please help me, because they won't ever reply to you. And then once you did your homework properly, and so you have a plan, you have to spend more time to basically keep saying to them, this is good, this is something that can work on every system, this is and this is better, I don't know, of other solutions. So this is really time consuming. We saw the same thing for Shaded. I mean, we spent 6-7 years discussing the thing on a mailing list and because so every time you post something, you have this review process, and in which they ask, I don't know, modify this thing, and then maybe they ask you to do something that requires a major review of your plan. So it requires a little effort. Yes. Okay. So how do we try to be general? So you have this PEL, so parent reload tracking. So this is slightly more detailed view of the thing. So it's basically tracking the thing using a geometry series, and you have two signals. One is load, and one is utilization. Load keeps track of the amount of time the scheduling entity, so the task, is runnable. So it's either running or just on a run queue waiting to run. And utilization is the amount of time it's actually running on the CPU. So so we have basically, as already said to Pepe, it's the load is actually depending also on the other task, because if you're running multiple entities and you are very much on the run queue, so waiting for the others to make space for you, basically your load will be increased by the other. Utilization, it's a better signal for what we want to do. And yeah, you have basically a scheduling period that is basically 100 millisecond window to do this kind of calculations. And what it gives you, this signal, it basically gives you a number scaled to 124, and that represents how big is your task on any CPU, on any frequency you're running at with our modification. So basically, if you have, I don't know, 800 tasks, it means that it's quite big. So you probably want to run that thing on a big CPU. And as I said, these numbers are both frequency and more scale. So it's pretty handy that you can use those without thinking, oh, I'm running the task on a little CPU at 300 megahertz or a big one. So you just use it, and it's fine. Well, you can actually just use it. You have to be aware that this thing is kept at the current capacity. What's the capacity thing? Capacity is basically the amount of CPU share that the CPU, the particular CPU, can give you in the future. So let's say that I'll get back to this, but the biggest CPU at the highest OPP will give you 124 capacity, so 100% of what you can do, and maybe a little CPU can give you, I don't know, 400, and that's and this means that if you run a little task on a little CPU at the highest frequency, that task can have utilization at least at max of 400. So you can just say, yeah, that's probably big. Let's put on a big, and then we'll see if how big it is. You have to just be aware of this thing. Okay, let's talk a bit about the energy model, because this is the crucial part, I guess, of the whole thing. So the energy model, it's pretty simple. It seems effective actually, but it's kind of simple because we just consider CPUs. So we don't we don't have any hint about like peripheral GPUs or memory. So it's just the CPU part that we model currently, at least. What it contains information about basically the capacities that you have different OPPs, so different frequencies of your CPUs, and also about idle state. So, well, you for sure already know that when your CPU is not running something, you can enter different level of idle states. Each one it's more power efficient, but maybe it requires more time to exit, so it's somewhat less performant. And so all these things trade off between the performance you need and both the OPPs and the idle states you can select. But maybe this is better explained with figures. So, okay. So here you have an idea of the kind of information we want to take from the architecture. So, well, that's not really informative anyway. This Juno, it's a development platform by ARM. It's a 64-bit platform that has A53 as little and A57 as big cores. And here, basically, you see how do we build the model concerning the OPP, so the performance state. To perform this kind of experiments, we just keep all CPUs online, and we basically use Sysbench, that is basically it's a busy loop workload that computes stuff that we don't care about. But the nice thing is that basically it saturates your CPU at any point you measure to, and it gives you a score at the end that you can actually use to say that's my capacity, max capacity at that OPP on that CPU. And that's basically what you get here. So here you increase the number of, those are cores because you basically run Sysbench with just a single thread. Those are those points, and then you run the Sysbench with 2 threads. And this means that basically you have power consumed here. So each line corresponds to a different OPP. So maybe this is, I don't know, 300 megahertz, and this is 1 gigahertz. And you get basically a performance score on this type of things. And then when you have all these points, you want to normalize those to 124. So this is the big cluster. So basically, the highest point here gives you 124, and all the others, also for the little, something relative to that thing. Yeah, so here we are basically, yes.
Measuring the power. Okay.
Yes, so you're
frequencies on different numbers.
Yes,
and the cores are the same frequency.
Yes, so basically you keep each line, you keep the same frequency. And
increase the number of cores.
Yeah, increase the number of cores. Well, increase the number of Sysbench threads. And you do this both for the big, I reported on the big here, but you have something like this for the little cluster.
And
yes, basically you get.
It's the number of cores, and you just modify the frequency. It's a linear.
So no, I mean it is linear for Juno, for this type of architecture. Actually, it's not always linear, and it is a big point. I plan to write the thing anyway. Usually, let's say the more general thing is that you may have different OPPs that are more or less linear, and then usually you have some kind of overdrive. So maybe the last, I don't know, 3 OPPs are like giving you somewhat better performances, but really high cost on power. So usually you want to go there really if you need to, because it's burning a lot of energy and power. And yeah, so basically you just use those points, as you said, and if you plot those, you see. Also,
So it's almost linear.
It's almost,
Some deviation.
yes, it's almost linear at least. You have two parts basically. The first one, it's almost linear, and then you have an overdrive stuff. And also the nice thing, I should have probably give a picture here or maybe later, is that if you overimpose this kind of power perf curves, as what how we call it, of the little and big cluster, you maybe see that they are basically overlapping a bit. So that means that you have to basically choose when you do a scheduling decision, if you want to run, for example, a little cluster at the overdrive of the last one, or maybe on the big one, because but if they overlap, basically this means that running here, so in the little cluster, the highest VP, it's a better decision on with respect to running at the lowest frequency on the big one, because you're basically doing more stuff with less power. Anyway.
And the assist bench is just the computing.
Yeah, I mean,
but it's not heavily used memory.
No, it's just computing
So
stuff.
the influence of memory cache.
And that's another interesting point. I mean, if you try to run basically this kind of if you try to plot this kind of plots using different workloads, you see that those curves basically are maybe more overlap, less overlap, depending on basically memory access or other influences. So let's say that is maybe not so suitable for any kind of workload that we can at the end run on the thing, because then this is I mean, when you run basically Android, you can have this kind of workloads, but you can have I don't know also workloads that are like heavily memory intensive. So basically this says that you are basically using a model that is not really perfectly, but I mean, it seems pretty fine at the end with different type of models. Maybe one thing you can do, and maybe it's also something to see, but to try to do, is like to, I don't know, run different type of workloads when you construct the model, and then maybe come up with a model that tries to address different type of workloads. So maybe it's not just skewed towards the high CPU intensive workloads. This is maybe something interesting. And yeah, from this model you get those things, and then you also need to extrapolate the contribution of your cluster. So basically the problem that you have is that each core can contribute independently, but then you have some kind of thing that you always pay when the cluster is on, and you can do this kind of extrapolation. I won't like give you too much information, for then you are interested, because we are maybe running quite a lot of time.
Yeah. Is it a theoretical course? It's not a real course, because when you start new groups, you don't see anything on you.
So
when you start new groups.
No, so in this kind of thing, you just run this sysbench and you run it basically to completion, or you can also limit, I don't know, you're running for 10 seconds, and after 10 seconds, you read the output. So it's basically the number, I don't know, of iteration that he was able to do. And this number of iteration is your score. So you can then normalize this thing, and this thing gets your capacity. So, and you just do it once. So it's not looping. Yeah. Okay, so this is the P part. Then you have to model the idle states of your platform. And this is simpler to do in some sense, because what you need to do is basically you turn on, so you turn off all your CPUs, and then you turn on one after the other to see how the contribution of a new CPU that is actually idle. So a CPU that is idle contributes to the power of your platform. So what we do is basically we isolate the cluster that we want to measure to the others. So we put all the stuff that we can put on, because we still need to run Linux on the other cluster. and then you just put the cluster that you want to measure in an idle. And what you do is that you can disable by writing on a sysfs entry all the other states that you don't want to measure. So what you do is basically, for example, in this platform, you have 3 idle states. So this is wait for interrupt. Then you have a core idle state associated to the different cores. And then basically, when all the cores of the cluster are idle, the cluster itself can enter a cluster power down. So it's a deeper idle state. And
So the system can interrupt only in the first,
yes,
in the blue one, but not in the middle and the last one.
no, you still get interrupt, but here it's called waiting. Yeah, waiting for interrupts, because it's basically it's an idle but still active, and you see this thing because basically you can here you see evidently that when you turn on once more CPU, so a CPU more, this amount of power you get is basically the contribution of the cluster. This is basically an active. It's an idle, but it's also still an active state, and you don't have the same thing when you see the core or the cluster power down, which means that they really are shut off.
My question is, when a core is in the last power down state and an interrupt arrives, does it wake up or not?
You need to do, let's say you need to do more stuff to wake up, because it's a deeper, really deep power state. So instead here it's basically waiting for interrupts to happen. And that means that this is a trade-off. Here you're burning lot of power more than here, but then you are more reactive. So to exit this state will require a lot of time. Yes.
For example, how much time do you need before exiting the last state? Do you have any?
This depends. I guess it can require, I don't know, quite a lot, like 3-5 milliseconds. So, but it depends. Not saying that this is the platform, but this is the order of magnitude. While this is really fast. Yes, this kind of idea. So yeah, basically you need these kind of things, and then you need to basically how we do is like we construct this model by separating the core part to the cluster part, because then you want to also decide, do I need to switch on the cluster or just CPU in the cluster? And you can do this by basically using those numbers. I won't also here get too much detail, but that's basically the kind of measures that we perform and that we use at runtime. Okay, so basically you know your platform, and so what's this energy-aware scheduling that we are working on? And this is has been posted before of this thing has been posted 2 weeks ago on email list. So right now it's under discussion for acceptance. The idea is that you just use the energy model and the information that PEG gives you about your task to evaluate the implication of your scheduling decisions. So that means how much power do I burn if I run this task on a big CPU instead of a little one, and also will I affect its performance or not? This kind of decision. You can just consult the model and do some math and come up with this thing. So our goal is to minimize energy while still getting good performance. And yeah, next slide I will detail about this good performance thing. What does it mean? So yeah, basically we want to minimize energy per instruction, and this is a big difference we have with respect to the default scheduler, where the default scheduler is just a performance only type of scheduler. Actually, without at least the work invariant stuff and the capacity awareness of the different CPUs, even the full one doesn't do always the right choice, the right performance only choice, because it doesn't have any notion of big a little. But anyway, let's say that we are fixing this part by trying to do something different. This is a nice thing, I guess. Yeah, so what does it mean, good performance? So it means that we try to do energy-aware scheduling only when we are not saturating the system. So as soon as we realize that, in this case, we are very conservative. So as soon as we realize that one CPU is fully utilized at the highest OPP, we just bail out from energy-aware and we do normal load balance. And that's because first you don't, as I said, you don't basically know if your task is really big or not because it's saturating its current capacity. So you can't say really much about it. And the other thing is that maybe, yes, you're saving something, maybe you don't turning on a big CPU, but then you're paying this thing much on performance. So let's say that in this kind of extremes, we just go with the normal load balance because it's probably the best we can do. So if we are above this thing that we call tipping point, we just start to spread tasks as the normal scheduler does. And yeah, when instead we are below, basically each time you add a new task to the system, or you're basically removing a task because its work is done, or maybe you have to see if you want to migrate tasks between CPUs, you consult the energy model, and you have also information about the utilization of task, and you can use this to try to do informed decisions. Okay, yeah, those are some numbers that we came up with for the last post on the mailing list. Those comes from another type of platform. It was an older one called DC2. So here you have big cluster. It's composed by two A15, and the little one is 3 A7. But it's basically the same kind of platform that you saw the energy model. And here, I want you to notice that here we just run on demand. So Linux has to be able to manage the frequency state of the CPUs. It has this CPU framework that basically tries to see how's the load of the system and then adapt the OPP to the current load. And we just use the on-demand governor. It's basically the default one that you find when you're running your laptop with Linux. And so here you see some numbers. I guess there are two things to notice. I guess is that the fact that we bail out when we are going to saturate the system is pretty evident here because this is basically us, and this is the energy you're consuming with respect to the current mainline scheduler. So here up until, let's say, this point, we are saving quite a lot by running a workload that is basically a synthetic one. So you're just running synthetic task that executes for some amount of time and then they sleep. But this kind of synthetic workload, let's say that it's a workload corresponding to 6% of the available capacity, total capacity of your system. So it's pretty light. And so you can see that we save somewhat good amount of power until we're going to saturate the system. Here, everything is basically referred to the biggest, so it's the 124 capacity value. So this thing here, it means that basically if you run something that is 44% of the total use of CPU, you're already saturating the CPU. So that means that we are already bailing out because I said that to be bailed out as soon as just one CPU is overutilized. And you may ask why you're consuming more, actually, why at least you're not doing the same thing. I guess, so here we just have energy, but here in the first row, we also have sysbench. So, and sysbench gives you a performance output. So you can actually say, okay, I'm performing quite good. So here you see that we are performing like more or less like 2 times 2.5 times.
Remember, it's performance or power?
No, this is power, energy. Power.
Energy. So you are consuming more than.
Yeah, so we are consuming quite a lot more,
You are getting more.
but we are getting more performance. So the performance score is not here, but we are, so trust me, we are getting like 2.5 and even more. And that's because the mainline kernel doesn't have any notion of micro architectural differences. So it means that basically every time you just run a sysbench, it will put most probably, because you have more little CPU on a little core. So at the end of the 10 seconds, you will do less operation. While we know that basically this thing is pretty big, and we put on the big CPUs and we run really fast. And that's something that is always like that. I guess the workload that is more close to a real application is MP3. So we use this RT-Up. This is a nice application that can run. You can specify the type of your task set, and it will run something that is resembling what you specified. So here with MP3, we basically produce a trace of a real MP3 audio pipeline on Android, and we then use RT-Up to run the same kind of thing. So here is basically what we save potentially if we run audio stuff on Android. So that's still quite good. Okay. So yeah, so let's recap. So yeah, with the modification we did, we can tell if a task is big or little using Pelt. We can tell using the energy model where it is more energy efficient to schedule it, and also indirectly, I mean, we can also control IO states, because we can just decide not to put a task on a cluster, and maybe the cluster can enter a deeper IO state. So is it missing anything that we don't control? What do you think?
Performance is not really defined, right?
Well, that's one thing. So we actually working on adding performance score also to this sysbench thing, and then we can really say here that yeah, we are paying more, but we are getting best performance. Or well, in the long run, we had to run real workloads on the platform. So we probably see. I mean, the performance aspect, we consider performance because we have a performance number in the energy model. So all the schedule decisions are done according to the trade-off. But I guess the other thing that we actually want to control is actually, so I said here that we are using the on-demand governance, so we don't have any control of what it's doing. Basically, this thing is basically another guy that is not a scheduler that sees some load on your CPU and then say, okay, I have to go at the highest OPP. We are basically indirectly controlling how it is behaving, because if you put more tasks on a CPU, you're going to generate more load on the CPU, and then you probably require more a higher OPP. But then we can probably select the thing right from the bat. I mean, we are controlling everything, so we have all information.
Scheduler, you just control scheduling decisions,
yes,
and out where to put tasks.
Yes.
Well, the frequency is completely another part of the kernel.
Yes, it's basically completely another part, completely another framework. It uses some information from the scheduler, for example, the load.
So the long-term plan is to integrate both.
Yes, and also by integrating both, I mean, the problem is that if they are not integrated, the only thing that this other part that is called CPU frag can do is basically have a polling thing. So I don't know if each 20 milliseconds it tries to sample the actual load and then react to this thing. While since we know what's the actual utilization load of your system, we can try to drive directly from the scheduler. And that's basically what we are trying to do, integrate both things to maybe do better stuff. So yeah, let's see if we can do better. Yeah, one thing that I didn't say, but that's just information. New information is that Android is using, let's say, modified version of on-demand called interactive. This is still basically using this polling thing to do different kind of decision, but basically it's the thing where we say here still holds because we are not in control of what it's doing. So yeah, we come up. Well, basically it's this Mike Tarquette from Linaro, this other organization. We are basically working closely with them. Basically, I'm working closely with him to to develop this thing, and yeah, we call it this shared BFS. It's basically the idea is that you want to create a new, let's say, CPU frac governor, so it's new CPU frac guy that basically it can directly be triggered from the scheduler to say, okay, I want both to run this task on this CPU, but also please go at this frequency because I know that this task will require this amount of capacity. And the idea is basically you want always to select an OPP that has enough capacity for your, so spare room for your task, because you don't want to saturate the thing as soon as you can. And yeah, I mean, the idea is that each cluster has different, what is called flag domain. It means that it can operate at different OPPs at the same time. And so you have always to, but inside each cluster, every CPU has the same, runs at the same OPP. You can run 2 CPUs, at least on our platform. There are also platforms that can do, but our platform, you can run the CPUs of the same cluster at different OPPs. So each time you have to take a OPP frequency decision of your cluster, you have to consider all the CPUs of your cluster. Right now, this thing works for CFS only because it just called from the shell normal path of the scheduler, but it should be fairly easy to extend this thing to other scheduling classes. Yeah, I guess there are a lot of details on this thing, but anyway, it's just here to say we are also trying to basically control all about the scheduler and his effect. Okay, so I don't know how much time we...
I was planning 1 hour, 1 hour and a half, so if you can go very fast.
Okay, I go very fast also because this thing you already told them, so anyway. So we are still here, and that's basically our contribution to the shared deadline. It's yeah, this is a bit of the story. So it started developing this thing on 2008 as part of the European project, Dario Fagioli and others. And then I switched in with my PhD. I started maintaining this thing, and I still trying to maintain it. Let's say help the real maintainer of the scheduler to address like patches and fixing bugs and these kind of things. Yeah, I guess the nice fact about this thing is yes, it's a real-time scheduling policy. So it is based on a model that is maybe not considering. I mean, it's quite general, but you always think, okay, you have to be really strict and you don't have to miss any deadlines. I guess the nice thing about this thing is that you can actually use it. I mean, you can also miss something. You can use it to just say that your task needs some kind of quality of service. And the nice fact is that if you use this policy, and this is something that is visible at the kernel level. So, which means that you can pass more knowledge from user space to the kernel to say, okay, I want this kind of quality of service. I have this kind of quality service requirements. What I'm saying is that instead of we do for CFS, that we need to keep track of utilization. This thing basically gives the kernel the information about the real, the imposed utilization of the task, and you can just use that to do your scheduling decision. So it basically makes the life of the scheduler much easier, I'd say. Yeah, it implements earliest deadline first, and then uses this constant bandwidth server over the thing. And I guess the cool thing here is the CBS, because yeah, if you have pure deadline scheduling can have some problem. I guess I mean, I can probably skip those things because basically, well, I go very fast. So here, basically, you have two tasks that basically almost saturate the loads, and with plain EDF, so deadline scheduling, you can schedule them without any of them missing any deadline. This is nice. Problem is that maybe your real task doesn't behave as you expect, so as your model expect. So, for example, this first task can maybe I don't know, just for waiting for a yaw can stop just after the second activation, and then be put back on the CPU, for example, when the third instance or the other task starts to run. But since it has an earlier deadline, we'll preempt it. I mean, we prevent this task to run, and we'll cause a deadline miss on the second task. So one task that behaves quite differently from what you expected can jeopardize the other tasks. Another thing that can happen is basically maybe this can be a software bug that you introduce in your task when developing it, and instead of executing for those 5 time units, it just goes straight because maybe it's a while one loop, and it will still cause problems on other tasks. With the CBS, that is basically implementing a reservation-based sharing, which means that the idea is that you have to allocate this CPU time, so this is your resource, to the running task. And one way to do it is basically you have to specify a runtime and a period for your tasks, and which means that each task will get this amount of utilization. That is a ratio between these two parameters. And this is the same kind of utilization, basically, that we saw before. The difference that with CFS, you have to, as I said, you have to track this thing, and maybe it's not the real one. The real one, where here it is enforced by the system. So it's a nice thing to have. It's additional information. Yeah, this CBS thing basically modifies the, let's say, the deadline that the scheduler sees of the task, and then those deadlines are used to actually schedule those tasks. The idea is that EDF uses the deadlines to schedule the task according to the priority, and then the CBS actually slow downs or throttles those misbehaving tasks. So it modifies those deadlines to basically ensure temporal isolation. What does it mean? It means that, for example, in the first example here, when the second task was missing the deadline, if you use CBS, what happens is basically at this instant of time, one of the CBS rules will be applied, and this deadline here will be postponed a bit. So that means that this task can run still and meet the deadline. And so this, I mean, the behavior of this task will be isolated with respect to the other one. And something like this happens, for example, also in the second thing. Oh, this is the wrong one. Anyway, it was the long-running one. And what happens basically after 5 time units, this is the runtime that you specified beforehand for your task. This task is being stopped, and the other one can run and meet the deadline. So this is the isolation thing. Yeah, some numbers basically just proving that the implementation is aligned with what theory says. Here we run the same kind of RTAP synthetic workload using this both deadline, shed 5 also RT fixed priority scheduling policy, and shed other, so CFS. Here you see numbers for a single processor run. And those are the percentage of deadline misses for different type of workloads that they saturate more and more the system. So you can see that, for example, with a workload that gets 90% of the single CPU, we should then can basically meet all the deadlines as we expect from the theory that says that this EDF it's optimal on uniprocessor systems. While using shed 5 or even worse, CFS, you can't expect to meet the deadline. So basically, this number here, it's that it means that the quality of service also of your single processor task will be much degraded, because it tries to it's basically showing them in the best effort thing. So it won't. And for the multiprocessor case, here you have four cores. You can see, so we know from theory that EDF is not optimal, so you expect some deadline misses here, but you still see that we are basically doing better than the other one, except for some configuration, but at least when the system is basically fully saturated, we get the best performance compared to the other scheduling policy. So that means that you can actually use scheduling also on multiprocessor systems. Here are some other numbers, and those comes from a real application. So we just use MPlayer playing. So it's a video player playing an high definition movie, and the metric we are interested into is this IFT, so interframe time. So basically the difference between the display time of the previous and next frame of the video streaming stuff. And usually variations on this in this IFT are not something that we want, because the video, basically when you see it, you will see it not playing smoothly. We needed to basically, as said, you had to specify a period for your deadline reservation, and the period basically corresponds to the real IFT that you expect from the video, given the frame rate of the video. So it's basically 41, 42 milliseconds. And so the period is this one. And while running the instance of FmpEG playing this thing, of MPlayer playing the video, we also run some background noise to see how, if the, let's say, the temporal isolation thing was really working. And you can see here, so here you have three lines. So one is the CFS, so it's the shell normal. So running this thing with shell normal together with 6 other instances of video streaming on the background. And you can see, so here you have the cumulative distribution function. So ideally, you want something that has probability 1 to finish computing before this 42 milliseconds. And this is only happening for shared deadline when you gave enough runtime to actually do the computing stuff that you need to do while decoding the video. While if you run the same thing with CFS, you see that you're having this long tail, meaning that there is a non-null and quite like 20%, for example, of times when you're like missing the deadline, so the video won't be so nicely played. The other thing to notice is that with shared deadline, you can like give your user this kind of guarantees while providing somewhat less CPU usage. So you can basically achieve, the idea is that you can basically achieve the same kind of niceness here using shared FIFO, giving high priority to just this kind of workload. But here, basically, you're not controlling the CPU usage. So basically, it says that you can potentially starve like sequence task or other things. Instead, with shared deadline, you won't do this. So this is another property. Okay, that's it about shared deadline. And I guess just conclude with open question that we have, and that's the whole point of, I guess, this thing. So for the energy aware heterogeneous part, so one big thing that we basically already a bit discussed is are there any other ways to get better understanding of user space? So how we get more information, I don't know, for Android or for anything that we run on top of the scheduler, that can be, I don't know, C groups or maybe other scheduling policies or whatever you can come up with. How do we convince those, I'd say, Android guys to give us more information, because they have those information in Android. And we have basically when we do this decision, we use just heuristics that right now are kind of not so, let's say, it can be probably simplified. Maybe also looking at the energy model, the thing that was saying before, that you have maybe some overlap to the two classes, you can maybe simplify your, we right now we put all those information in the energy model, and then we just use it, the full thing at the runtime. Maybe you can just simplify some of the paths that you know that you won't go in, because there are not many, they are not sent to let's be taken. And so this is simplified, or else, I don't know, maybe you can simplify the CPU energy model, and then with this simplification, it means that you can maybe use, I don't know, another model for the GPUs or anything that you see that is affecting your system, because GPUs or no, also thermal influences, especially in mobile phones, you have to keep track of the heating of your CPUs, because you are basically holding the thing on your hand, so you will feel much more thermal than running on a notebook. Yeah, so I don't know. Yeah, I mean, those are stuff that it will be nice to have a look at, but we don't. I mean, we as a developer in ARM, you probably don't have much time to work on, because you want to basically release the thing. So it's more a search type of, and since the thing is reasonably plain good already now, maybe it's not like highest priority. And also here, maybe it would be nice to find some way to let the user choose the, let's say, add, I don't know, some kind of knob to say, okay, I want to, I don't know, now I want to go fast, because I don't know, I have, I'm recharging my phone while playing video, or here I want to really be power efficient, because I know that I won't be able to charge my phone in like till this evening. So you maybe want to have, because right now the model just does one thing, or at least two. I mean, it is energy efficient as it can do, or power efficient, power. So this is maybe the stuff that we are done. I'm sure there are a lot more, but anyway. And for the deadline scheduling part, I guess, well, those questions, for example, what happens if my budget requirements vary? How do I adapt to the thing? Or what if I have shared resources? How do I manage these things? Well, those questions, maybe from a pure theoretical part, you already have a lot of answers. But as I said, it's not always easy to translate what the theory says to actual implementation in Linux, because you have still those constraints. So for me, those are more like practical stuff. While I think that you, when start trying to implement something, you maybe come up with I don't know, simpler theoretical answers to the same question. So maybe it's still interesting. Yeah, this is around, I don't know, groups scheduling. So it may be handy to be able to keep in the same kind of queues to overp the multiple tasks, because I don't know, you're running a virtual machine that has several threads to schedule on. And basically those two, it's something that I hope I will work on in the near future. So how do I use this thing over the stuff that we are, I mean, the awareness, both about frequency and micro architectural differences on your system. Because right now you can just specify Q over P over, so this P is basically time, expressed in time units, but then you don't know the real amount of CPU time that you will need if you run on a little CPU or on a big one. So how do you use the information you basically have at the kernel level to basically use the same kind of stuff. So did I cover everything? I don't know. I guess yes. I don't know. Oh no, that's beer. So in the thing I also said that I cover beer. So yeah, I mean that's the idea is that every good technical discussion always happens in front of a good beer, and this is really true for the Linux conferences. When you go there, you basically, yes, during the day, it's like you're talking with those people and there are presentation and stuff, and then they organize those events and you start drinking and people relax, and then you can really talk about stuff you want to implement and an aspect that they usually pay for the beer, so that's also a nice thing. But okay.
Very like to beer. But I think.
Yes, that's it. So
Okay,
if you have any
thank you.
question, yeah.
Any questions, general, specific? Anything?
So you mentioned that you do not consider the energy consumption of devices.
Mhm.
Or devices. So it seems that on a mobile platform, for instance, it has a very big impact on the consumption of the system overall.
Mhm.
Is your phone on, or is your mic on, or your screen on,
Yes.
and things like this. So is there any way to cope with this? Any hope to cope with this? And do you know if the energy reduction you gain from targeting the CPUs is really something important with respect to the overall energy, or is it?
So basically, what? Yes. So basically, yes to both questions. The one that we always, I mean, when we develop this thing, we just measure the CPUs, but then you run real workloads. You have basically, I don't know, a video game playing on a thing that is with the screen on and this kind of stuff. So you also model user interaction with automatic testing, and you can see that with or without this kind of solution at the scheduler level, it makes quite an impact still. Because I'd say that CPUs are more and more basically reaching the point where they are the same CPU you find on desktop and this type of stuff. So it means that if you save quite a lot of power on your CPUs, you will see this at the other side when the thing is actually used. And we just target CPUs because, for example, the screen or mic or this kind of stuff are basically controlled by Android. So the idea is that we do our best at the CPU side, and then Android will say, okay, this is more, I mean, it's how the user wants, I don't know, the screen brightness, these kind of things, in more a framework type of, framework as Android type of decision. So that's
Also, the network, I think, is controlled by.
Yes,
Android,
yeah, it's
so Wi-Fi, power.
yes.
And
So it's not really something that you maybe want to control at the scheduler, the scheduler level, kernel level. So it's still.
there is no automatic mechanism inside the kernel for deciding the power of the Wi-Fi.
Not really that I know of. I guess it's more Android that controls this thing. Yes.
For instance, your scheduling decision could have an impact on how you are using the devices, your peripheral devices. For instance, the network controller,
Mhm.
if you broadcasts that are communicating at the centers, and you can switch off the network while you are separated, then you have to.
Yes, so that's exactly what I was saying when I said that I think that we need more information from Android, and this is an example. Maybe Android knows about this kind of relation between tasks to make more informed scheduling decisions. So basically, at the kernel level, it's kind of maybe you can do, but it's kind of tricky to extract those information. You have to basically construct those information at runtime, while Android maybe already knows that and can basically say to you, "Oh, look, all those tasks, I don't know, group those tasks together and schedule them like a group because they are basically interacting with each other." So yes.
In fact, one of the biggest problems in work.
Can we make one question here from Oran?
You, as a really technical know this, but it's of course overhead. And usually developers don't like a lot.
Yeah.
Developers. So, of course, you can do everything by just looking at what the task is doing. But it's very difficult to do a general model that will take into account all the characteristics of the task.
Yeah, for example, one thing that this is another field, but one thing, for example, they do on NUMA machines, where you have like different accessing time for different banks of memory. They basically keep track of the page faults, for example, and they try to migrate tasks closer to the memory that are accessing. This is something they do at kernel level, but I mean, it's somewhat not always easy to come up with this thing.
Do you think really that if you want energy consumption saving, you don't have take care to your embedded system? Because on ARM computer and big data is not the same as general multicore, and you can have real save energy consumption if you are not closer to the architecture.
Sorry.
Android is global, but is it?
Yeah. So in fact, the idea, as you said, is to build a general model that then can be instantiated on a little or other processor.
Yes. So
and you work on the general model.
So
and then the big little is just one specific instance of the general model.
Yeah. So basically, the discussion that we are having on the mailing list is not just between us and the maintainer. It's basically between us, people working for Intel, people working for IBM, so Power Machine, and they are basically all trying to come up with best solution that is basically working potentially on different type of architecture. So, and that was the difference between the first type of approach, where it's focused just on big little ARM processor, and this new one that is tries to be as general as we can.
For instance, Intel approach is not the same as ARM approach with the algorithm of dual core.
Yes, I mean,
yes. So they try to make an effort to come up with a general solution which can fit Intel or ARM, because they want to maintain one single Linux kernel code base.
I mean,
otherwise they would just have two different Linux, and at some point they will diverge. And this is a little bit what happened with Android. Android has its own Linux.
Yeah.
And at some point they try to merge what is going on in the Linux mainline inside Android, but they have their own.
Yeah, right now maybe they realize that, and so right now they're basically trying to go for a solution that has some kind of they're quite like to be at least behind in the near future. So they don't want to basically go away too much from the mainline.
Your own version of schedule. So, because every time they release something, and now they release something every month, basically.
Yes.
You have to check if your patch is still applicable to new kernel. And if it's not, you have to do the application. And if they changed something very important in the scheduler, for example, you have to go there and rewrite part of your code and retest. So it's a lot of work.
So
it's half of the time of this PhD was
yes.
devoted to keep the patch in sync and try to convince the developers of the mainline to accept this patch.
So basically,
and now finally, just before we finished it, the patch was accepted. So now we are relieved. We don't need to keep care of this because it's the Linux developer themselves that will run the automatic testing and they keep track of all the modification, make sure that everything is consistent.
Yeah,
so even for ARM, which is a big company, maintaining a separate version of Linux is too much.
Yeah, also because I guess the problem is that you want to say, okay, right now I'm quite confident that in the next, I don't know, 3, 4, 5 years, I will be compatible with those. I mean, I can run Linux on those systems, and this is not maybe quite like to happen if you are like working on something that is separated from Linux, because I mean, to get you a rough idea, the Shadowline I think was around, I don't know, 15 patches, so it was quite simple and small. But to maintain this thing, it required at each like effort to rebase the new kernel was I don't know, 2-3, I mean at least 2 weeks, because it's changing quite a lot, the scheduler code, and then you have to be always comfortable with saying, okay, you have I don't know, locking problems, so everything that can happen. So it's quite a lot of effort. You don't want this. Yes.
Il y a une question à Oran. On va pas remettre le son pour que puisse la poser. Parce qu'on est en diffusion en écran avec Mastodon.
Actually, it's.
You hear us?
Yes, please.
So the question was, can we set a little core to idle state while other little cores are in active state?
So the question: can you set a little core to idle state while the other little core are active?
So
Active.
this depends on the platform itself. So we saw two types of platform. One is TC2, and the other one is Juno, that is the newer one. So for example, on TC2, there were just two types of idle states. So there were the WFI and the cluster shutdown. In that case, you basically can just, if you have one CPU that is active, all the cluster is basically active. Instead, with Juno, you also have a pair core idle state. So the core that is basically are not active can enter that particular core idle state that is saving more power than the WFI and less power than the cluster. So yes, you can be in intermediate configuration.
So it depends on how this little core is instantiated in the specific platform.
Yes, depends on that.
Okay.
Also for the OPPs, so the FREX, for example, you can have in this kind of in our kind of implementation, you have the same OPP for the two clusters. So each cluster can have a different, but each core in the cluster it's a different OPP. While, for example, Qualcomm, I guess it has different OPPs, or even for the different cores of each cluster. So it depends.
So who is that now produces this big little? So everybody, basically.
Yes,
Samsung.
Yes, everybody, and I guess
Qualcomm.
Yes.
Yeah. So ARM doesn't produce anything.
No,
It's
ARM
just,
doesn't produce.
yeah,
No, it's
just
the IP.
Just the idea.
Yes.
Okay, some more questions?
Good. So it's good. No.
Okay. You? Anything else? No? Okay, anyway, if you want to talk with us, we are a little bit around for some more time, so you're welcome. Okay, thank you. Thank you. I'm going to stop the video.
Okay.